how to perform range queries efficiently, in an AVL tree, right? This is sort of, once you get the AVL tree working, which is enough challenge, then you have to get this done. So this, coding-wise, is not very difficult. It's not very long, but the logic is a little difficult to get. Okay, so let me try to explain this again. Like the way you should write your binary search tree functions is using recursion. Then it becomes a lot more easier to process. So the way to think about it is, suppose you have a node, and let's just say this node is start, and you have a range. So I'll refer to this range as, I'll just call it low and up. So a range is like two numbers, right? Or it's two, in this case, I forget, it's two words or something. It's like the lower part of the range and the lower end of the range and the upper end of the range. And let's just say you want to count how many nodes in the subtree rooted at start lie in this range. So let's say you want a function that does how many nodes in the subtree rooted at start in this range. Right? That's the question that you have. So naturally what you do is you're going to compare the key of start to both low and up. Right? And you'll see that there are three possibilities that can happen. So I'll call this case 1, case 2, and you'll see why I'm drawing it this way. Case 3 is I'm just thinking of this is low and this is up. So I'm just drawing this on the number line so that you can see the comparisons. Make sense? I'm just drawing these numbers on the number line, right? Low and up. You're trying to find out how many nodes of the subtree lie in this range. So first you compare start, right? Or start, the key of start. So I'm just going to call the key of start x. Okay, so I'm just saying that x is equal to start arrow key so that I don't have to write start arrow key all the time. So x could be here, x could be here, or x could be here. Does this picture make sense? Right? You're comparing the keys, right? So you're saying the key at start compared to low and up. Yes? No? Is this making sense? Okay. So what happens in case 1? I claim that you can make a simple recursive call then. Yes? You want to go right. Because you know that anything to the left of x is going to be here, so it's not going to lie in the range. So you only have to make a call to the right. So you just make a recursive call. So let's just say you have some function. So suppose your function is something like range start low up, right? This is some function. You just make a recursive call to start arrow right, and then the other parameters will be the same, right? So you don't need to go to the left side. So it's like you can completely ignore that entire portion. And this is where this is more efficient than a tree traversal. A tree traversal will just walk through the entire tree, ignoring the values. Does this make sense? Sort of, kind of? Yeah? So what happens in case 2 is you do range start arrow left. Because over here, everything in the right side, the right subtree of x, is going to lie here, and so it's not going to lie in your range. Does that make sense? So again, if you think about it, if you think about what makes binary search efficient, It's because binary search makes one recursive call either to the left half or the right half, right? And therefore it's logarithmic time. Something similar is happening here. It's making one recursive call. It's only going down left or going down right. Now this is where you have a problem, because now the values could be both in the left and in the right. And if you make a recursive call on both sides, you're going to start having some problems. So you have to now what happens is, okay, so go ahead.
You do a different function that will just go through and like count it down each side until you find it?
Almost, yes. So you now have to call a different function both in the left and the right. Okay? So let me this picture makes sense? So now we're going to make two calls, function calls. One to look at things in the left side, one to look at things in the right side. But these are going to be sort of like custom calls for this situation. Okay, so let me now write, I'm going to so I'm going to give two functions. I'm going to call the first function range only low, and this is going to call start arrow left and has one parameter low. I'll explain what this means. And I have a second function which is range only high, or only, instead of high, let me call it up. Start arrow right, up. Okay, so what do I should call it low and high, not low and up. I was thinking lower and upper, and then I didn't want to write the ER, so sorry. But okay, what does this mean? So in this situation, there are some keys in here that are in your range, some keys in here that are in your range. But let's look at, if you look at all the values in this subtree that are in this range, they only lie over here, right? Because everything has to be less than x. That makes sense? And everything in this subtree here only lies over there. Because everything in the right subtree is more than x. So what has happened is that your range has split into two parts. Now observe that all keys that are more than low in the subtree rooted at start arrow left. All keys that are more than low in the subtree rooted at start arrow left are in the range. Okay, let's parse the sentence. What am I saying? I said any key that is more than low in the left side must be in your range. Because everything in the left side is less than x. So if it's more than the lower, it must be in the range. So when you're going to the left side, you only need one argument, just the lower end. You don't need the upper end. And this is now going to actually make things more efficient. So what they're saying is that you know that in this subtree being in the left subtree, every key that is more than low is in the range. In the right subtree, everything that is less than up is in the range. Yeah? So what range only low does, it's a new function that counts the number of nodes in a subtree that are more than low. So all it does is it's looking as how many things are more than low. Does it make sense? Now this function I'm now going to solve by recursion on itself, and this is actually going to be kind of like a binary search style thing that I can only make one recursive call. Okay, so is this making sense? Right? So again, like the logic takes some time to understand, but once you get the logic, the code is actually quite short if you do it through recursion. Okay, so now let's see how to implement this function. The range only up is going to be analogous, and I'm not going to discuss it. Basically, left is going to be replaced with right. Okay, so let's try to solve the range only low. And now let's just say this has two arguments that are called start and low. It's not the same start as here. This is another function. Okay, so there's some other function here. Okay, so this is start. Okay, so and again, the natural thing is to compare start arrow key with low and see where it lies. So what does this function do? It counts the number of nodes in the subtree rooted at start, counts the number of nodes in the subtree that are greater than equal to, or you can make it greater than or greater than equal to, it doesn't matter. Let's keep it greater than equal to. Does this make sense? All right. So now we'll see that there are two cases here. So case 1 is start arrow key is less than low. Right? And you're trying to count everything that is more than low. Case 2, sorry, let's keep low over here and start arrow key. So this picture should hopefully tell you what to do next. Does this, am I making sense here? Like, is this, so what are you going to do now? So let's look at this, right? So in this case, start arrow key is less than low. So, yes? So there is no low value you're searching for, right? So you're just counting everything more than low. But what you're saying is you don't need to look at the left subtree here, because everything that is in the left is going to be to the left of start arrow key. It's less than start arrow, so you can ignore that. You make one recursive call here to the right. Okay? What happens here? Yes?
Recursive call to the left and the right.
If you make a recursive call to the left and the right, then those will make two recursive calls, then you end up with linear time. But think, how can you make just one recursive call? But you're going to have to store some other information. Yes? Okay. You mean the subtree size on the right? Exactly. So in this case, everything that is more than start arrow key must be in your range, and everything to the right is more than start arrow key. So instead of making a call there, if you knew how many nodes were there, you could just add that to a total. And so if that is stored at each node, you can just look it up. I'm going to say this again. This is the complicated case. So I'll say this again, then I'll write it. So the first case, is this clear? You can ignore everything on the left subtree. Yes?
How come low or start arrow key, if it's less than low, how come we're going to the right subtree?
You're trying to count everything that is more than low. If you look at start arrow key, everything to the left of start arrow key is less than start arrow key. So you don't have to, so you can ignore all of that. You only have to look at things on this side, and that's what the right subtree has. Now in this case, there are things in this subtree and this subtree that are in the range. But observe that this entire subtree is in the range. Yes?
I'm still confused. Like, when we first called this function, it started with x being like in the middle of a range, and that was the call to the left that are all less than?
No, so there are two different functions here. There are actually three different functions I'm implementing.
But isn't this the one that's, like, we have x, we call this for the values that are less than x, right?
No, no. So say it again. It's a different start. Start is different. It's a different function. So think of it there being, instead of, sorry, just a second. There are going to be three different functions. Function 1 is, I give you a low and up, you count how many things are in the range. Function 2 is, I just give you a low, count everything that is more than low. Function 3 is, I give you an up, count everything less than up. You're trying to solve the low up problem. You'll make calls to this function that just has a low and just has an up. Does that make sense now? So in this case, everything above start arrow key is in the range. Hence, this entire subtree is in the range. And so all you need to do is, if you know it's total, you don't have to make a recursive call. So if you store subtree sizes, now why is storing subtree sizes a pain? Every time there's a rotation, things change. So you have to fix all of those things every time there's a rotation and an insert and everything, right? So you have to be very careful that you're maintaining all this information. But it's efficient once you figure it out. So then you can actually just make one recursive call to the left side and add the number of things on the right. So it's just one recursive call again. And if you think about it, all of it is in log n time because you're just going to go down the tree once. Yeah.
For case 1, you said that we can basically ignore, we don't do anything and that happens. But isn't there the possibility that if you go...
No, say it again. It's not that we don't do anything. We make a recursive call on the right side. You're not going to stop.
You're still calling a function in case 1.
You're going to call this function, exactly. You're just going to call the same function recursively.
Okay, cool.
At the right. And here you're going to make one recursive call to the left, but then you're going to add the total. You also have to add the value of, add the node start. That's another, one gets an off by one error because you forget to look at start.
What's the base case? Like, where does it break out?
Yeah, where does it break out? Yeah? When it reaches a leaf. Or when this is null, you can just output 0. Right? Another thing is, usually for these, the base case is when start is null, output 0. I'll write this down, but is this clear? So this is, sort of kind of, when you go and look at it, it should hopefully make sense. But this is how a lot of fast ranges in databases are implemented. Because you just make one log n depth call. Yeah?
For case 2, you said you make one recursive call to the left before you add the right subtree. Is that what you said?
Sure. I mean, it doesn't matter, right? It's like let me write something down, and then hopefully this will be clear. Okay, so in case 1, you just make range only low, start arrow right and low, right? That's your one recursive call. Sorry for those sitting here, as you can't, this is right. Okay? So this is case 1. So in case 2, here's what you're going to do. You're going to return range only low of start arrow left of low plus, I'll say start arrow right arrow subtree size. So I have a new field which stores the subtree size plus 1, and the 1 is because of start itself. Right? So this is a new field storing subtree sizes. This has to be maintained during all rotations, which is your main pain point. Okay? So in addition to maintaining heights, you have to maintain subtree sizes, but you will see that when you do a rotation, maintaining subtree sizes, again, it's just a constant number of operations, right? So for every pointer that changes, or every child or parent that changes, you have to go and change subtree sizes everywhere. Yes? Good question. So What if you created a helper function that went and computed the size at each time? Yeah? But it's not even based on the height, right? I mean, the total number of nodes in a subtree, the only way to figure that out would be to traverse the entire subtree. Yes, or actually it would depend on the number of nodes, which is even worse. So that would default to a linear time solution. That would almost default to just walking through the entire tree. So you have to store it so that you can get it with one operation as opposed to making a function call. Because if you made a function call, then your function call was going to have to go and compute the size. How long does it take to compute the number of nodes in a tree? It's linear time. Like it's going to have to go in and like go through the entire tree. It's a good point. You will save some, but it's not going to be enough to process like a million operations. You'll save something, but storing it is going to be much more efficient. And I think that given the number of queries I'm giving and the size of the tree, it's probably not going to help you that much in runtime. Yes?
Get a pretty good estimate by knowing the depth of the tree and knowing that it's balanced, right?
But it's an AVL tree, so actually the range of sizes is actually quite large. It's like in between like, you know, the hth and the h plus 1th Fibonacci number. And that's actually a fairly large range. Multiplicative, it's like, you know, you'll be off by quite a bit.
And you want an accurate.
Yeah, I want the exact answer. I want the exact answer, right? So, yes? How do you keep track of the subtree size? Okay, so this is every time there's an insert. So you remember we had this discussion on the height. Every time there's an insert, where does the height change? You have to perform that same sort of logic for subtree sizes. Every time there's an insert, the subtree size changes for all the ancestors. So that's how you update it on an insert, which is easy. The painful part is when there's a rotation, subtree sizes will change because children parent pointers are changing. So that's something that you'll have to you work out. You'll see that if you see the logic for changing the children, the subtree size is almost identical. Yeah?
When we're like, I think retracting is the word, going back up the tree after an insert.
Uh-huh.
How do we know whether or not the node or ancestor we're at needs its height increased? Because sometimes it does, but sometimes it doesn't.
Yes. That's right.
Is there a trick?
There's always a trick, right? It's always a trick. So what is the height? The height at a node is the maximum of the left and the right plus 1. So don't make a function call for that, but just it's the maximum of the left height, the maximum of the right height plus 1.
Assume the children are correct.
So or rather if only one of the children would have changed, and if that's changed, yeah, you assume the children are correct.
And then follow-up question, would it be crazy if instead of creating my own recursive function, I just went to like the bottom half of the insert function and then just like put code there? Or would that be an alright method of?
No, that will to update the heights. Yeah, no, that's what you should do. You should be careful if you make a recursive function. Anytime you make a recursive function that makes calls to both children, that's going to be a linear time because that's just going to then traverse the entire tree. The only way that you get efficient, like logarithmic style, is think of binary search, right? You make one call either to the left or to the right. You cannot afford to make two calls. So in this whole code, there's only one time that two calls are made, but these are to two different functions, each of which only makes one recursive call each time. It's a bit subtle, and that's how you get log n time. Yeah?
So for each node, would we want to store the size and the height, and then the balance factor, we could just use the heights of the children?
Exactly. Exactly.
We only need those two.
You only need those two. So it's very easy to get 5 points in this assignment and pretty hard to get 10. Like, I mean, there's a lot of work in getting to 10, but once you, these are like, hopefully you see the basic building blocks of this, right? One is the AVL tree, which requires maintaining heights. Then there's maintaining subtree sizes. and then there's sort of patching together all this code on top of it. Once you get the subtree sizes correct, this part is actually, I've pretty much almost written it, right? It's just going to be like some recursive calls. It's very short. But the gotchas are usually when you're doing subtree sizes, you'll often get off by 1 errors. You'll forget to look at the start, like you'll forget to add that, and then those are the pretty hard to track. Yes?
Would you write a linter to check manually whether your tree is in correct state while you're debugging it?
That's what I had done. Like I had actually, for the AVL tree, I had done like, I think maybe about 10 or 15 nodes, and I just checked it manually. By hand, I just checked that it was correct. Well, actually, you can, right? So this is where if you have the simple 5-point version coded up, then at least you can easily make a function called count subtree sizes using that, and then you can use that to sort of cross-check. So that would, yeah, that's, I think, I probably also did that. I think I did that first, and then in the AVL tree, just to check the structure, I had done it by hand. Yeah? So again, I mean, I repeat, like, don't go to the AVL tree until you get the basic version done. Right? The basic version, again, is like, I'm pretty sure you're all at the stage where 1 day's work, you sit down and you can crank it out. You can crank it out in a day, and then you might debug it, for like another day or something, but you should be done. This part, there are lots of moving pieces. Okay? So, one of the reasons to give you an assignment of this kind is so that you deal with lots of moving pieces of code, right? And then that's sort of the practice. Once you do it a few times, then you start getting, no one is, I guess. Some people are very good at it. I'm not very good at it, but you do the practice, and at least you can start doing it, right? So there are multiple moving pieces of code. Do not try to sort of do everything and then go back and debug it. Build it step by step. Make sure everything is correct. Does that make sense? Like, because for every piece, you just check, is this working or not? Like, if you look at this range searching idea, this has nothing to do with AVL trees here. This works for any binary search tree. It's just that in an AVL tree, the depth is low, so therefore it's efficient. So you could code all of this stuff on a normal binary search tree and make sure it's working for small trees. Yes?
What's the best way to check that our AVL tree is working properly?
That, I think that it's to just manually like draw it out, use the visualization to see the tree, and then print out the tree in pre-order traversal, and then like reconstruct the tree by hand.
So I've been like, I mess it up, and then I reverse it, trying to like, and if it comes out the same way, then I assume that it works, or is that not?
I guess that would also be fine, but I would actually just like draw the tree for small examples. Yeah, I think that usually if your AVL tree is working correctly you have to make sure that you're inserting in all possible cases, right? Because there are these 4 cases in the AVL tree, and you have to do all if you keep inserting, like, if you always insert 10, 20, 30, 40 in increasing order, you will only be doing one kind of rotation. So try to insert in lots of random orders, or delete from random places. The assignment does not need delete. But it's still, it's not much more effort to have the delete, because I've already given you the delete code, so you can just delete from the AVL tree. And that's why being able to reconstruct the tree from pre-order traversals is useful for debugging. That you can just do by hand. Like, you just print it out and then just draw it on paper. Okay? There are lots and lots of pitfalls in this assignment, right? So there are lots of places where things go wrong. So that's why, do it slowly, step by step. And that's why I think that for this assignment, there's more than 2 weeks, at least since when it came out. Okay? All right, any questions? Any questions about that? Okay, it is a bit overwhelming, so I readily concede that, but by design. All right? Any other questions about this? Homework 2, anything? Yes?
Homework 2, when is it the makeup due?
Do it soon.
Oh, okay.
Do it now or not now, but now-ish, right? Like, please finish it this week, definitely, right? Because I don't want to have a situation where my TAs have to deal with regrades from throughout the quarter in the last week, which is what happens when I relax rules, right? So yes.
Can you really re-explain makeup for homework 2? I wasn't doing it on Thursday.
There's a Piazza post on. It's the same rules as usual. Yeah, same rules as usual. Okay. Good. All right. So that was range searching. But maybe I'll just step back and say that this is like one of the places where binary search trees really show their strength, in that there are lots of complex